Alright, we're going to be tackling Unit 4 FRQ. So, we have a dart is launched toward the center of a sphere that hangs from the ceiling by a string. As shown in Figure 1, the masses of the dart and the sphere are mz and 5mz respectively, and the center of the sphere is initially at a distance L below the ceiling. The dart is traveling horizontally with a speed of v initial immediately before it collides and sticks to the sphere. After the collision, the dart sphere system swings upward on the string until its center of mass reaches a maximum vertical height of delta y above the position at the time of the collision. So the dart is initially traveling fast enough that it can be considered to be traveling horizontally before colliding with the sphere. So what are we answering? So A, on the axis in Figure 2, sketch a graph of the total kinetic energy kd of the dart system as a function of time over the entire range shown on the time axis. The collision occurs at time tc and reaches its maximum height at time tmax. So what does this graph represent? The graph is the total kinetic energy of the dart plus the sphere system, and the time runs from before the collision, after collision, to the maximum height. And the collision occurs at time tc, and the maximum height will occur at t max. So because we know that the total kinetic energy is going to be constant, right? So that means from kd, right. So from kds we have 1/2 mv v initial squared. So we can draw a horizontal line at a constant non-zero value. So yeah, let's just draw that. Because we know that t is going to be less than tc, and the dart is initially moving at speed. Okay, so the dart is initially before the collision, the dart is moving at v initial and is moving horizontally. So yes, the collision is at tc, and yes. Now they want us to, what am I saying? So then during the collision at t is equal to tc, then the dart sticks. Okay. The collision is perfectly, and here the collision is perfectly inelastic, and mechanical energy is not conserved. So that means that some of the kinetic energy is transformed into thermal, sound, also internal deformation. So this drop has to be instantaneous. So there's a sudden drop. We can actually make this here. So it's a drop at tc. And then, yeah, there's a drop. And then after this, it's going to be instantaneous. Instantaneous drop. And then, okay, so and then after this, from tc to so t is between tc and tmax. Well, this is when the dart and the sphere, they move together as a single system. The dart plus the sphere system, right? And then this is also when the system swings upward, and also the kinetic energy is converted into gravitational potential energy, and also no further energy loss assumed after collision for this part, right? So there's going to be a smooth continuous decrease in kinetic energy. And then here at Tmax, this is when the system momentarily, actually we're kind of running out of space. Okay, so the system momentarily comes to rest and that's when the speed is equal to 0, right? You have KdS is equal to 0. So you have a horizontal line before TC, then you have a sudden vertical drop at TC, and then you have a smooth curve decreasing to 0 at Tmax. So now, what do we want to do? We want to derive an expression for the speed of VC of the dart sphere system immediately after the dart collides with the sphere. Express your answer in terms of MD, L, and V initial and physical constants as appropriate. So we know that, during the collision, we have external forces. We have the forces of FG, we have FT, and these are going to be vertical. But we also know that the horizontal momentum is conserved. So because we know this, we can write the momentum before the collision. So before the collision, we know that only the dart is moving. So because of that, we know that P initial is equal to mdv initial. This is before the collision, and then after the collision, we can write we know that after the collision, that's when the dart sticks to the sphere, right? So that means we had to find the total mass after the collision, the m total. That's gonna be equal to, up here, it was it was md and 5md. So this is md. Well, actually, let's make this pink. md, and then this is 5md. So when they combine, that's just gonna be the total mass. That's gonna be md plus 5md is equal to 6md, and we know that the final speed is gonna be equal to vc. So that's the velocity of like the collision, c for collision, and that means that p final, pf, is going to be equal to 6 md times vc equal to mass times velocity. So now we can use the conservation of momentum, right? Conservation of momentum. So then we have mdv initial is equal to 6mdvc. So now we can cancel out the md. So you just have that vc is going to be equal to v initial over 6. All right, and then it's just over 6. So now let's go on to the next part. Derive an expression for the maximum vertical height delta y of the dart sphere system above its position at the time of the collision. Express your answer in terms of md, L, and v initial and physical constants as appropriate. So we know that after the collision, we know that, so like it hits it, right? So like the dart, okay, so that's like pre, and then this is like post, right? The dart, and then it like swings up to this, whoa, this is messy, like here, and then this is at like, that's like delta y, right? Okay, wait, that's like messy. This is like delta y. Like the thing is like stuck in there. All right, and then it went up there. So after the collision, there's no, we assume that there's no energy loss assumed. And then the motion is upward along an arc, and also that the mechanical energy is conserved, right? So then we can write the kinetic energy post the collision. is equal to 1/2 6m d v velocity collision squared. That's just the 1/2 mv squared. So we can substitute in that vc is equal to v initial over 6, right? So okay, whoa, wait, actually that's ugly. We have that, right? So then we have that k is equal to 1/2 6m dv initial over 6, right, squared. And then we have k is equal to 1/2 6m d d v initial squared over 36. K is going to equal to md v initial squared over 12. And now we want to also write the gravitational potential energy at the max height. So we're gonna try to find UG. So that's gonna be this is at max height. Whoa. So that's gonna be U is equal to 6 d times g times delta y. So that came from U is equal to UG. Okay, well, UG is equal to g delta y. Now we can use the conservation of mechanical energy. Because we can use this, we have mdv initial squared over 12 is equal to 6 mdg delta y. No, none of that. So we can actually move this down a little bit. So now we have v initial squared over 12. We cancel d from both sides. And we have 6g delta y. Now we're just solving for delta y. So 6 times 12 delta y is going to be v initial squared divided by 72g. So we have this v delta y, box all our answers. And chat, I realized I made like a mistake. This is curved because you know why? Because kinetic energy is equal to hold on. Kinetic energy is equal to 1/2 mv squared. Oh my gosh, this is squared, so that means it's quadratic and it's parabolic. That makes sense because it's being curved, it's quadratic. So that means it's not linear. So it's a curve. And anyways, okay, so now that we fixed that, now we can move on to part B. So 3 more darts are launched, one at a time, at the Earth. Each dart has the same mass, md, and collides with the sphere with the same horizontal velocity, v initial to the right, with the sphere initially hanging at rest on the string. So the darts are made up of different materials, however, and each behaves differently when it collides with the sphere as follows. So the stick dart, this dart sticks to the sphere and remains stuck in the sphere. After the collision, the dart sphere system swings to its maximum height delta y stick. Bounce dart. This dart bounces off the sphere and then moves backward to the left. After the collision, the sphere swings to a maximum height delta y bounce through the dart. This dart passes all the way through the sphere and continues traveling to the right. After the collision, the sphere swings to maximum height delta y through. Indicate which of these 3 darts result in the greatest maximum height for the sphere and justify your answer. So let's analyze each of these. Let's start off with the stick dart. And what does it say? So the stick dart remains stuck to the sphere, and then it swings to the maximum height. So this means that it is a perfectly inelastic collision, right? And because of this. This is because the dart, it sticks to the sphere, and then afterwards they move together afterwards. So that means that the dart, it transfers all its horizontal momentum to the system, right? So that means we can write that P initial is equal to md V initial, right? And then that means that the final momentum, because it's perfectly inelastic, right? So it's just going to combine. So that's md, the dart, plus the 5md that we had earlier. So we had, remember earlier we had 5md. The 5md from, this was 5md. And then you have that md. But this was 3 more darts that were launched. Right. So you have that times V, and then this is equal to 6mdv. So this would result in a moderate speed for the sphere. Also remember that each dart is its own trial. So that means you don't count the old dart that we stuck earlier. So it's just md plus 5md. So now through the dart. Okay. So for through the dart analysis, this passes all the way through the sphere and continues traveling. After the collision, it swings to the max height delta y. So this means that the dart is still moving forward, and also that some momentum remains with the dart. So that means that the sphere receives less momentum than the stick case. Therefore, we know that the sphere's speed is smaller than in the stick case, and that the maximum height is smaller. So, and now if we analyze, low-key we're kind of running out of space here. So let me actually just okay, so now let's analyze the bounce dart. So the bounce dart bounces off the sphere and then it moves backwards to the left. After the collision, so it goes the opposite direction, the sphere swings to the maximum height of delta y bounce. So for the bounce dart, it bounces backwards. So that means the dart reverses direction after the collision, and the final momentum of the dart is opposite in direction. So the change in the dart momentum is the largest. That's because we have delta P is equal to md times VF minus V initial. So then VF is going to be negative. So then the magnitude of delta P is greater than md V initial. So then we can use Newton's third law. The sphere receives an equal opposite impulse, and also the sphere gains the greatest momentum. So because of this, this one has the largest post collision speed. So the bounce dart is going to be our answer. So then, for our final answer, we can write that the bounce dart undergoes the greatest change in momentum because it reverses the direction, and by the conservation of momentum, the sphere receives the greatest impulse there, and and therefore has the greatest speed immediately after the collision. And since the sphere's kinetic energy is converted into gravitational potential energy as it swings upward, the sphere reaches the greatest max height in this bounce dart case. So to decode this question more is what we're trying to find out was what can we do to make the sphere go higher. So after the collision, the sphere swings upward, and then at the very top, the sphere is momentarily at rest, and then all of its kinetic energy is transformed into gravitational potential energy. So the height depends on how much kinetic energy that the sphere has right after collision, and then we know that kinetic energy, it depends on the speed, right? So that means that the sphere that leaves the collision with the greatest speed will have the greatest height, which is intuitive. Greatest speed will rise the highest. So we're looking at the final speed, right? And what we were looking at was so we know that the sphere starts at rest, right? So the only way it can start moving is that if the dart has to give it momentum. And the key idea is that the more momentum that the dart transfers to the sphere, the faster the sphere moves. So now we're basically asking which dart transfers the most momentum to the sphere. And then this is the most important part, is that the momentum transfer is the change in the dart momentum. So we know that the momentum transferred to the sphere is equal to the change in the momentum of the dart. So that means that delta P sphere was equal to negative delta P dart due to Newton's third law, equal opposite reaction. So we can compare how much the dart's momentum change is in each case. So again, in the stick dart, we see that the dart comes in moving right? And then the dart sticks to the sphere, and then the dart is no longer moving independently. So then the momentum change of the dart is P initial is positive mdv initial, and then finally it's smaller to the right, So the dart loses some momentum, which goes to space. So it moves at a moderate speed because it only gets a decent amount of momentum. But then when we look again at through the dart case, when this happens, the dart comes in moving right, and then it passes through and it keeps moving forward. So then the momentum change of the dart is the P initial is going to, whatever. P initial is positive MD V initial. The PF is going to be still positive MD V initial, but like a little bit smaller. Yeah, a little bit smaller. So that means the dart loses a little. Okay. Momentum. So the sphere gains only a little momentum. So the sphere, so in the end, the sphere moves slowly, slowly, and reaches a small height, right? And then for the bounce dart, what happens was it came in moving right it hit the sphere, and then the dart bounces back to the left. So then the initial momentum again was initial is MD V initial, and then the final is negative. So then it means a change in the momentum here. We can see that's delta P MD VF minus V initial, or aka PF minus P initial. We can plug those in right here. So we have these, and then we have that this is a very large change. So we know that the dart didn't just slow down. What it did was it changed direction, and when it reversed direction, and this is the largest possible momentum change. And by Newton's third law, the sphere receives an equal and opposite momentum change. So that means that the sphere gets the most momentum, the sphere leaves the collision the fastest, and the sphere rises the highest. And like you can also think of this like when you're bouncing balls, like why bouncing balls transfer the most momentum. So like think of someone catching balls. When someone gently throws you a ball, you barely move. But when someone throws you a ball that sticks, you move more. But when someone throws a ball that bounces back at you, you move the most. So same thing with the physics here. We can think about the momentum and change. So that's why when it goes through, it's going to be the smallest. There's going to be the smallest momentum transfer, and the sphere speed is going to be the smallest, and the max height is going to be smallest. Okay, so let's actually write that down. So, okay. So, for the stick, it's going to be medium. Okay, wait. I can actually write that down here. So the dart type momentum transfer sphere speed max height it's gonna be the smallest, small, medium, largest, and hopefully that clarified some things for you. All right, thanks for listening to FRQ.